Hello everyone, I'm Greg Karlovitz from the Hydrologic Engineering Center. Welcome to our course on statistical methods in hydrology. This video is part 2 of 4 on the topic of simple linear regression, and we'll discuss constructing a linear regression model. Let's get started. Solving the line of best fit is an optimization problem. We want to find the parameters beta naught and beta 1 that make the line agree with the points best. We measure the agreement between the points in the line using an objective function for our optimization called the sum of squared errors. This takes each residual, squares it, and adds them all up. Squaring the residuals is mainly done for mathematical convenience, but the best side effect is that the estimators found in this way have simple distributions. Applying this technique is called least squares estimation. The goal of least squares estimation is to find the value of the coefficient and intercept that minimizes the sum of squared errors. Here, we rewrite SSE in a slightly different way, but recognize that the term inside the brackets is just the residual, observed minus predicted. We want to minimize this term. Every traditional discussion of least squares estimation shows this derivation, but I'll be brief with it. I do like this result a lot because it's really elegant. To find the value of each of the parameters beta naught and beta 1 that minimize SSE, we take the partial derivative of SSE with respect to each parameter and set them equal to 0, and then solve for beta naught and beta 1. I'll spare you the calculus and get right to the solution, which is very satisfying. The equation for beta 1 can be simplified even further as the covariance of x and y divided by the variance of x. I showed you the equations, but in practice you'll rarely use them. Most statistical software has regression built in so that you can directly estimate the slope and intercept terms without ever looking at the least squares formulas. Even the chart function in Microsoft Excel can compute a regression slope and intercept automatically. It also has a better regression analysis tool available in the data analysis add-in that produces results more similar to standard industry applications such as R, SAS, SPSS, Maple, and so on. The R Statistical Programming language is quickly becoming the standard for statistical analysis. If you're familiar with programming in any language, R can be very quick to learn. Even if you don't have extensive programming experience, there's a wealth of online help for R, and the documentation for R is excellent. Notice here that there's no appearance of the least squares equations, only calling the LM function on some data and then getting a summary of the model. We will talk about the information that a regression model provides next. This is an example of the regression output from Excel's data analysis add-in. The bottom part of the table is called the ANOVA Table for analysis of variance. Much of the information shown here is the same as shown in other tools like R. They all vary a little bit, but all of the most important stuff is here. It's a lot to take in, but we'll dive into only the most important items. Discussions and interpretations of this information are available in many statistics texts and in many other places online. Let's blow this table up a little bit. The first thing I want to identify is the R-squared value for the model. This is also called the coefficient of determination. In simple linear regression, this is one of the most important metrics for your model's performance. This value can be thought of as the percent of the variability in the y values that's explained by the model. Larger values are better, and the range of values is between 0 and 1. In this case, an R-squared value of 0.85 means that the model explains about 85% of the variability in the data. The value below it is the adjusted R-squared, which becomes valuable in multiple regression. Keep this value in mind when you work with multiple regression models. Next, let's look at our regression coefficient. This is the estimated value of beta 1 using the least squares equations. In a good regression, this value is significantly different than 0. If the coefficient is 0, then the values of the predictor variable don't matter when predicting the response variable. The difference is tested using a t-test, and the result of this test is shown in the p-value column. The p-value states the probability that a coefficient of this magnitude could be different than 0 by random chance only. Note that in this case it's extremely small, which means that the evidence is very strong that the coefficient is not close to 0. This is good news and means the coefficient is worth keeping in the model. Normally we choose a level above which we won't call the difference significant before we start modeling. Normally, we choose a value like 0.05, and if the p-value is greater than this, we don't consider the coefficient significantly different than 0. One more metric to keep an eye on is the p-value for the model ftest. The model ftest checks whether the model is significantly better than a model that only has an intercept, in other words, no predictor variables. Small p-values like this reject the hypothesis that an intercept-only model is better. If you have a significant predictor coefficient, you'll almost always find a significant result for the ftest as well. This becomes more important in multiple regression when you start adding in extra predictors. However, it's always good practice to check both the coefficient significance level and the model ftest significance level. One final important value to consider in this table is the standard error of the regression, shown below the adjusted R-squared. This value is the sample estimate of the standard deviation of the error. Small values are better. This is the regression output from R, and it also contains all the important things that we're looking for. I like that it's a little more concise than the Excel data analysis output, but still contains everything I'm looking for. The model R-squared is on the lower left, labeled multiple R-squared. The predictor coefficient is in the table labeled coefficients under estimate and next to the predictor name. The significance level, or p-value, is shown as the last column of the table. R also uses little graphical codes to show what the range of significance level that the p-value falls in. In this case, we have 3 asterisks, which is a p-value between 0 and 1 in 1,000. The model ftest p-value is in the very lower right on the last line of the model output. Finally, the standard error of the regression is in the middle of this output in the first row of the last grouping of output, labeled residual standard error. In this video, we discussed constructing a simple linear regression model. 2 key points to take away from this video are: least squares estimation is a technique used for finding the slope and intercept of a regression line that minimize the error between the line and the data, and regression model output provides several important metrics for evaluating the quality of the fitted model. Thanks, and tune into the next video in this series on simple linear regression to learn about checking model assumptions.